Sige. So let's continue what we were discussing last time. No, we were talking about BJTs or bipolar junction transistors. I'm going to repeat something that I already mentioned last time, and these are the steps in analyzing a common emitter transistor circuit. So just go through this again. The first step, we apply KVL to the base emitter loop to determine I sub B. So that's the first thing that we're going to do. We're going to try to determine I sub B. Now, when you apply KVL to the base emitter loop for silicon transistors, just to simplify matters, you can assume a base emitter forward voltage of 0.7 volts. And what happens is the base emitter loop will be really just a diode circuit. No? You analyze it like you would analyze a single loop diode circuit. So the second step is, okay, based on the value of I sub B, take a look at the value of I sub B. If I sub B is equal to 0, that is the base emitter diode is not conducting, then right away we conclude that I sub C is equal to 0, that is the transistor is cut off. Because if I sub B is equal to 0, that means either the base emitter is reverse biased or the forward voltage is not large enough so that it is greater than the turn-on voltage of the base emitter diode. So if I sub C is equal to 0, automatically your output will be equal to VCC. Okay, if I sub B is greater than 0, it won't be less than 0, no, because of the direction of the diode arrow. If I sub B is greater than 0, the next thing we do is we assume the transistor is in active mode. And when the transistor is in active mode, this equation applies. I sub C is equal to beta times I sub B. We now try to solve for VCE. And we solve for VCE by applying Kirchhoff's voltage law to the collector-emitter loop. We examine the value of VCE. We compare it to VCE SAT. If VCE is greater than VCE SAT, then we know that the collector-based junction is still reverse biased. It is still reverse biased, and therefore our transistor is really in active mode. And therefore, whatever value we compute for IC as step 4, it is correct. Okay, for reference, for silicon transistors, VCE SAT is 0.2 volts. If we find that VCE is less than VCE SAT, then we know that our transistor is saturated and that the value of VCE must be equal to VCE SAT, no? And based on that, we have to recalculate the value of I sub C. So these are the 5 steps. So I'm going to repeat the previous example, get the chance to discuss this example more thoroughly than last Tuesday. Okay, so fill up the table below. So I have a transistor, silicon, VCE SAT equal to 0.2 volts. VBE active equal to VBE SAT equal to 0.7 volts. In other words, the voltage drop across the base emitter diode, whether it is in active mode or in saturation mode, will be equal to 0.7 volts. And then beta equal to 100, supply voltage equal to 5 volts, collector resistance 1K, and base resistance 10K. Okay, so last time, we already said that when Vin is less than or equal to 0.7, our V out will just be equal to 5 volts. So here, this is just going to be equal to 5 volts and 5 volts. Why did we say that? Well, if Vin is less than 0.7, then this diode, the base emitter diode, will not conduct, and therefore your base current will be 0, and therefore your collector current will also be 0. If this voltage is 0, then V out will just be equal to VCC, which is equal to 5 volts. And that will remain the case until Vin is 0.7, because when Vin is 0.7, that is at that point where this is just about to turn on, but your base current will still be equal to 0, and therefore V out will just be equal to VCC. So let's analyze now what happens when we increase V in further. So let's say V in is equal to 0.8 volts. So at V in equal to 0.8 volts, okay, we analyze our base circuit. What does our base circuit look like? So we have V in. This is RB, which is equal to 10K. And then we have our base emitter diode, which is equal to 0.7. So we analyze this. We just apply KVL here. Okay, you get V in minus RB times IB. Okay, this is your base current. Okay, minus VBE equal to 0. But we said that VBE is 0.7. Okay, this is 0.8. V in is equal to 0.8. So I can compute for I sub B. I sub B will be 0.8 minus 0.7 divided by 10K, and this is 0.01 MA. Okay, assume active. Assume active. Yun, no? Tapos na tayo dito sa step 2. No? Okay, we computed already for, actually, no? Step 1, we computed for I sub B. Step 2, we already saw that I sub B is not equal to 0. So nandito tayo ngayon sa step 3. We assume that the transistor is in active mode. So if it's in active mode, IC is equal to beta times IB, which is now going to be 100 times 0.01, you're going to get 1 MA. And VCC, okay, using incremental KVL, VCC minus RCIC is equal to V out. So V out is equal to VCC minus ICRC. So this is 5 minus 1 MA times 1K. So this is just going to be 4 volts. Okay, so what's the next step? I compare VCE to VCE SAT. And I see that VCE is greater than VCE SAT, meaning to say, the assumption that our transistor is in active mode is valid. And so tama lahat ng kinompute natin so far. So ibig sabihin tama itong mga values na na-compute natin so far. So since VCE, which is equal to V out, is greater than VCE SAT, V out is equal to 4 volts. So this is going to be 4 volts. Okay, so let's continue. So at V in equal to 0.94 volts, so we just follow the same procedure. Okay, so I get IB. So this formula, essentially this formula, no? Except that papalitan natin yung V into 0.94. IB is equal to 0.94 minus 0.7 all over 10K. So this is now going to be 0.024 MA. Again, no? Assume active. So we assume active. So IC is equal to beta IB. So this is now going to be 2.4 MA. And what is V out? V out is equal to VCC minus ICRC. So this is 5 minus 2.4 M times 1K. Okay, so 2.4 M times 1K is 2.4 volts. So 5 minus 2.4, I'm going to get 2.6 volts. Now, don't forget to do your check. No? So check if really active. No? So since V out is greater than VCE sat, so 2.6 is greater than 0.2, then V out is really 2.6 volts. So this is 2.6 volts. Okay, here's what I want you to do. Can you compute for these two values on your own? No? Kung sino man nandito. Take the next few minutes. Paki-compute nga yung value nito at saka nito. No? Please don't look at the slides kasi if you look at the slides, nandun na yung sagot. So just try to do it on your own. Okay? So take 2 or 3 minutes. Ginagawa ba ninyo? Baka hindi nyo ginagawa. Okay, do you have an answer for both already, Albert or Mel?
Sir, dalawa pa lang po, sir.
Yung dalawa lang, no? Yung 1.1 volts at saka yung 1.15 volts.
Yes po, sir. Meron naman po.
How about you, Mel? Or nakakahabol ka ba? Mel, have I lost you? Andiyan ka pa ba?
Yes, sir. Well,
Do you have an answer?
not yet done pa po.
Sige. I'll give you mga one or 2 more minutes, no? And then let's proceed. Okay, Mel, can you tell me what you computed for either 1.1 or 1.15 volts input?
Na-stuck po ako dun sa may ano ba to? IB ba to? IB. Na-stuck nga po ako dun.
Na-stuck ka? Sige. Anyway, sige, Albert, what about you?
Sa 1.10 po, I got 1 volts. 1 volt po. Tapos po sa 1.15, I got 0.5 volts.
Okay. Okay. That's correct, no? Both are correct, no? So, sige, gawin natin yung 1.15 para kay Mel, ano? For the benefit of Mel. Okay. So at Vin equal to 1.15 volts, okay? So again, no, step by step natin, Mel, Vin, ito, no, using KVL at the base loop, kasi ang una, sabi natin, ang una natin gagawin is determine I's of B, no? So using KVL at the base loop, you have Vin minus IB RB minus VBE is equal to 0. So our IB is Vin minus VBE over RB. So this is 1.15 minus 0.7 divided by 10K. And if you compute for that, ang magiging value is 0.045 MA. Okay? So the next step is we assume active. So anong value, Mel, anong magiging value ng IC if we assume it to be active?
So 1.15 volts po, sir.
Yes, so dito, no? Kung IB is
Okay,
equal
okay.
to, dito, ito na
0.
yung IB. No?
times 100, so usog dalawa, 4.5 MA.
Okay, 4.5 MA, no? So kung IC is 4.5 MA, this is assuming active. Ano yung V out natin? Okay, sige, let's just do it. V out is
0.55
Okay.
volts minus 4.5 M times 1K, 4.5 volts, 0.5 volts.
Okay, that's right, no? So this is VCC minus ICRC. So this is 5 minus 4.5 M times 1K. So lalabas this is 0.5 volts, no? Okay, pero actually, hindi pa tapos yun, ano? Pag nakuha mo na yung 0.5, ano yung dapat mong gawin, Mel?
Compared to VCSAT.
I-compare mo sa VCSAT. So we see that VCE is greater than VCE SAT, ano? Or yeah, V out, no, is greater than VCE SAT. So ibig sabihin tama ito. Tama yung active and therefore tama rin to. Okay? So tama itong 0.5. Okay. So I'm going to put the answer of 1.18 and this is going to be 0.2 volts, no? So ito, this is still active, ano? Pero punta tayo dito sa 1.2. Punta tayo dito sa 1.2. Okay? At Vin equal to 1.2. So compute natin uli yung IB, no? IB is equal to Vin minus VBE all over 10K. So this is 1.2 minus 0.7 over 10K. This is going to be 0.05 MA. Ang IC ko is going to be 100 times 0.05. So this is going to give me 5 MA. Okay, this is again, no, this is assuming active. Assuming active, no? And my VO is 5 minus IC times RC. This is going to be, ano magiging value ng VO ko?
0.
0, no? So VO, which is VCE, is not greater than or greater than VCE SAT, no? So anong ibig sabihin ngayon yan, no? Kasi ang VCE SAT ko is 0.2, no? So VCE is not greater than VCE SAT. Ano ibig sabihin yan? So anong ibig sabihin nito? Ibig sabihin assumption is wrong. Mali yung assumption. No? Ibig sabihin, saturated na tayo. No? Transistor is saturated and VCE, which is equal to VO, is VCE sat, which is equal to 0.2 volts. So actually, ito 0.2 volts. So, meron tayong nakitang pattern, ano? This is V out. This is V in. Okay. Nakita natin na yung output natin is VCC. This is 5 volts. Until that point where V in is 0.7. No? Pag tinignan mo, no? Until the point where V in is 0.7, ang output natin is 5 volts. Okay. Habang lumalaki yung V in, lumiliit yung V out. So if you notice, habang lumalaki yung V in, lumiliit yung V out. And it goes down linearly. Okay. So nung umabot na yung V in ng 1.18, so ito, this is now 1.18. Ang value ng V out ko, okay, is 0.2. Kapag linakihan ko pa further yung V in, hindi na ito bababa. Hindi na siya bababa. Ang mangyayari, may iwan na lang siyang ganun. So if you take a look at your operating modes, okay, this is cut off. Mula rito hanggang dito, this is active. Tapos mula rito hanggang dito, this is now saturated. So ang significance ng saturated is kapag linakihan ko pa yung V in, hindi na bababa yung V out ko. It will stay at 0.2 volts. Okay? Nakuha nyo yan? Did you understand that? That's very important. No? That's why it's very important. Lagi nyong gagawin tong check na to. Because this is what will tell you whether your transistor is saturated or not. Okay? So I hope that's clear, no? Kasi yun, no? That's a very common mistake among the students in 1, 2, 3, no? Or students for that matter that are introduced to the transistor for the first time. Nakakalimutan nilang check-in yung condition for saturation. They just think that the relationship IC equal to beta IB, they think it is true all the time. No, it's not true all the time. It is only true here in the active mode. Once you are saturated, it is no longer true. Okay. So again, these are your answers. So let me just again state that this is cut off. This is your transition from cut off to active. Okay. This is now active. This is your transition from active to saturation. And then here, this is saturated. Ito yung mga transition points, no? These are the transition points. This is a transition. This is also your transition. So actually, itong value to, this value of V in, this is the exact value of V in that will cause your transistor to shift. No, it is the shifting or the inflection point from active to saturation. Okay. Now I'm going to discuss with you the transistor as an amplifier. No? So can a transistor be used as an amplifier? Okay, if you take a look, the previous exercise, so itong exercise na to, no, where we have V in and V out, the transistor is in the active region when V in is from 0.7 to 1.18. No? So ito yun, no? From 0.7 to 1.18, andito siya sa active region. No? So if I have a signal, kung meron akong signal na hindi lalampas ng 1.18 ang pinakamalaking value, hindi bababa sa 0.7 yung pinakamaliit na value. So here's an example of that signal. So ang value nito, hindi bumababa sa 0.7, hindi lumalapas sa 1.18. If I plot the output of that, ang magiging output niyan will be between 5 and 0.2. When your signal is 0.7, the output is 5. We computed that. When your signal is 1.18, bababa yung output natin to 0.2. Ito magiging itsura ng output. So yung signal ko at 0.7, pansin nyo 0.7, ang output ko is 5. No? Yung signal ko na 1.18, ang output ko is 0.2. No? And between that, okay, your signal will vary proportionately to the input. So you just notice that when your signal is increasing, your output is decreasing. When your signal is decreasing, your output is increasing. Now, anong napansin nyo? There's a gain. Meron tayong tinatawag na gain. No? You're going to study gain in more detail in EEE 131. No? So suffice it to say at this point that gain is just the rate of change of output versus change in input. So it is delta V out over delta V in. So if we take a look, ano yung gain? Ano yung gain dito? Notice, no? Your input, peak-to-peak value, tignan lang natin yung peak-to-peak value. The highest voltage is 1.18, the lowest voltage is 0.7. So what is that? 1.18 divided by 0.7, no, minus 0.7. Magkamali ako, no? That is 1.1 volts, no? Sorry. No, sorry, that's 0.48 volts. No? So ang peak-to-peak value nito is 0.48 volts. Pag tinignan mo yung peak-to-peak value nito, 5 minus 0.2, the peak-to-peak value is 4.8 volts. So if we get delta V out over delta V in, actually that is negative 10. Negative 10, no? Kasi delta V out is 0.2 minus 5, no? This is 0.2 minus 5. Delta V in is 1.18 minus 0.7. So this is going to give me minus 10. So nakikita nyo how the transistor amplified the input. The output is almost a reproduction of the input, except that it is reverse in phase. We call it reverse lang niya in phase. Or piniflip niya yung positive, ginagawa niyang negative, yung negative ginagawa niya positive. And the smaller the value of R sub B, the larger your gain. As a matter of fact, usually sa mga transistor amplifier circuits, usually itong R sub B is 0 or almost equal to 0. And when you make this 0, actually your gain can be in the hundreds. Pwedeng in the hundreds siya. Okay. Typically for a BJT, you'll get a gain of 200, 300, or whatever. Any questions? Any questions so far? So I just wanted to introduce the transistor amplifier to you. So nakikita nyo paano nagkakaroon ng gain? Okay. Okay, ano mangyayari if we input a larger voltage, no? So nakita natin dito, okay, we applied a voltage na 0.48 volts peak to peak. What if I applied a larger voltage? So let's take a look at what will happen, no? So imbis na 0.48 volts peak to peak, ang in-apply ko is 1.5 volts peak to peak, no? So take a look at this. This is 1.5 volts peak to peak. Okay. My output will be 5 volts whenever V in is less than 0.7. That is, it will be at cutoff. And my output will be 0.2 volts whenever V in is greater than 1.18. So when V in is greater than 1.18 dito, between these 2 points, my output will be 0.2. On the other hand, when V in is less than 0.7, these 2 points, my output will be 5 volts. So this is how my output will look like. No? Ideally, dapat ganito yung itsura niya. That is, if the amplification were good, dapat ganyan yung itsura niya. Pero natatabas siya rito sa 0.2, natatabas din siya rito sa 5. And so we are not amplifying anymore. So this is what we call distortion. Distortion. The output is clipped. And that is what transistor biasing is all about. I'm not going to teach you about transistor biasing because transistor biasing is something that you'll take up again in EEE 131. But I just want to introduce the concept to you. No? You notice that my input signal has a DC component and has a time varying component. So my input signal is composed of 2 voltages in series. One is fixed and one is time varying. No? Kaya ito yung input signal natin kanina, no? Between 1.18 and 0.7. No? Ang DC component niya is ito, no? 0.94 volts. And ang time varying component niya is peak 0.24 volts positive minus 0.24 volts negative. No? So that is what this signal consists of, ano? A DC component, a DC component and a time varying component. Yung gusto nating i-amplify is just this. This is what we want to amplify. Okay, but we know we will not properly amplify this unless we add this. So kailangan idagdag natin itong component na to so that this can be properly amplified. And that is what you call biasing the transistor. So I just threw that in just to give you an idea of how you can properly set up an amplifier. But if you are finding it hard to wrap that around your head, don't worry about it, no, because it's not something that we're taking up yet in EEE 123. I just wanted to you to appreciate that. Any questions so far before I continue? Okay. Mel, nakakahabol ka ba? Are you finding it hard to
Yes,
keep
sir.
up?
No, I'm fine.
Okay, sige. Okay, so we saw the transistor, you can use it as amplifier. You can also use a transistor as a switch. Okay, yung amplifier, ginagamit natin yung transistor in active mode. It has to stay in active mode. No? Pag nawala siya sa active mode, patay na yung amplifier natin. No? Yun ang nangyari rito. No? Dito nawawala na siya sa active mode. Dito, it is already cut off. Dito, it is already saturated. Wala na siya sa active mode. Kaya wala na, sira na yung amplifier natin. No? We have to keep it in active mode, just like here. No? For this entire voltage range, your transistor stays in active mode. No? Now, when we use a transistor as a switch, it is either going to be in cutoff or in saturation. Okay? Bakit, no? When this transistor is saturated, the voltage across this transistor is 0.2 volts. No? So if this is saturated, if saturated, VCE is 0.2 volts, assuming it is silicon. No? So this is for silicon. Kung switch siya, if it were a switch, the voltage is equal to 0 volts. Yeah, 0.0 volts. No? That's confusing, sorry. Zero volts. Kung malaki yung VCC, ito negligible. So parang zero na rin siya. So this is negligible. So this is approximately equal to 0 if VCC is large. So if this is saturated, it is like a closed switch. Okay. On the other hand, if this is cut off, sorry. No. If this is cut off, ibig sabihin IC is equal to 0, then this is an open switch. Okay, so what are we saying here? No, you can use an input voltage to control the load, to turn on and off the load. No, and the input voltage should be such that if you want to turn off the load, the input voltage should be low enough so that this is cut off. If you want to turn on the load, the input voltage should be large enough so that this is saturated. So in this particular example, okay, a silicon transistor with beta equal to 100 is to be used to control a 500 ohm 20 volt load. So determine a suitable value for RB if a 1 volt signal, so itong VIN natin, a 1 volt signal is what we will use to turn on the load. Okay, so to turn off, we can just say absence of a signal, no? Or 0 volts. To turn on, 1 volt. No? Okay, so how do we compute for R sub B? Okay, the first thing we want to do is compute for our IC SAT. No? Compute for IC SAT. That is the collector current when your transistor is saturated. No? So if this is IC SAT, okay, what is IC SAT? If we do an incremental KVL here, this particular loop, no? So VCC minus IC SAT multiplied by RL, RL is my load resistance, minus VCE SAT is equal to 0. So we're assuming that this is saturated. That is why IC SAT is flowing. So IC SAT is the current that flows when your transistor is saturated. Okay, so IC SAT is VCC, okay, minus VCE SAT all over RL. Okay, in this particular case, this is 20 minus 0.2 over 500 ohms. And I'm going to get 39.6. MA. Okay. Now, what is my base current? No, that will produce my collector current. Let's say on the verge of saturation. So on the verge of saturation, in other words, active pa siya, pero about to saturate. So on the verge of saturation, IB sat is equal to IC sat over beta. Hindi pa siya talaga saturated, doon pala siya doon sa transition point. No? That's why you can still apply IC is equal to beta times IB. And this is going to be 39.6 milliamperes divided by 100. Okay, and I'm going to get okay, I'm going to get 396 microamperes. 396 microamperes or 0.396 milliamperes. Okay, what must my base current be for this to be saturated? So that means that for transistor to be saturated, I sub B should be greater than or equal to IB sat. But I sub B is equal to V in minus VBE all over RB. That is KVL, the base emitter here. No? Okay, and we want the transistors to saturate when you have a 1 volt signal at the input. So this is 1 minus 0.7, no? V in equal to 1 minus 0.7 all over RB. No? I want this to be greater than IB sat. No? So 1 minus 0.7 over RB should be greater than IB sat. Okay. If I compute, it's in IB sat, if I compute, okay, I'm going to get RB should be less than or equal to 0.3, 0.3 divided by 396 micro. Or RB should be less than or equal to 757.6 ohms. So basta't ang value nitong R sub B, is less than this, then my 1 volt input signal will be enough to saturate the transistor. So as an engineer, meron tayong tinatawag na tawag dito, safety factor, no? We will not, if you're an engineer, you're not going to use a value exactly equal to 757.6 ohms, no? Because what if nagkataon, for example, mas maliit pala yung beta ng konti. So what you're going to do is you're going to choose a value that is substantially less than this. No? Now, there's a disadvantage to making it very small. You're going to learn that later on. It has something to do with switching time. But you're going to put some safety factor. No? So, for example, me, if I were designing this, I would choose. Let me add another page. So I would choose R sub B, let's say, equal to 700 ohms. Equal to 700 ohms. So anong ibig sabihin nito, no? You remember my graph? Ice of C versus ice of B. No? Na habang active, ganyan. No? And then, pag saturated na, ganyan na siya. No? So this is active. No? So this is IC equal to beta times ice of B. And then this is IC sat. In this particular case, we computed IC sat. This is 39.6 MA, no? Which is equal to 39.6 MA. No? And this is IB sat, which in this particular case is 396 microamperes. No? 396 microamperes. Itong point na to, this is RB equal to 757.6 ohms. No? But I don't want to operate at this point. I want there to be some factor of safety. So ilalagay ko somewhere here, for example. No? So dito, let's say RB is equal to 700 ohms. Diyan ko siya ilalagay. In other words, I will choose a value of IB that is slightly higher than IB sat para lang sigurado, para lang may safety margin. Ano? So this is like my safety margin. Just in case, for example, yung beta ko pala was smaller than 100 or something like that. Did you understand what I was trying to say? Okay. So that's engineering, no? Yun yung tinatawag nating engineering judgment. It's not something that you develop instantly. It's something you develop over time. Okay. I just want to point out these useful current relationships in a transistor. So remember, these are your transistor currents, IC, IB, IE. And if you think about this, if you think about the transistor as a quote-unquote supernode, no? You think about this as a supernode. So you think about that like a supernode. Then ang ibig sabihin yan is IE, the current leaving, should be equal to the current entering, IB plus IC. So you have this relationship. And if this transistor is in active mode, then you also have this relationship IC is equal to beta times IB. So if I combine these two equations, I get IE is equal to IB multiplied by 1 plus beta, no? Just combining these two, eliminating I of C. No? Kasi ito, I of C is equal to beta IB. No? Itong I of C is equal to beta IB. So I of C, itong I of E will just be beta, 1 plus beta IB. No? Okay? By just combining these two. Then I get this relationship. No? This is the relationship now between IB and IE. And I also get this relationship. This is a relationship between IC and IE. Okay? And then if you take a look at this, note, if beta is very much greater than 1, so kung malaki-malaki yung beta, IC is approximately equal to IE. Because if beta is very much greater than 1, then beta over 1 plus beta is approximately equal to 1. And IC will approximately be equal to IE. Okay. So okay, these relationships are going to be quite useful to you. No? Okay. So in the material that was presented by Dr. Sison in one of his videos, okay, he talked about a more stable transistor current source. No? Because remember what we said about a BJT? A BJT in active mode is a current controlled current source. No? Diba? Sabi natin, a BJT in active mode is a current controlled current source. And when you have this particular circuit, for example, where this is your load, okay, so this is VCC, that's your load, RB. This is IL, that's your load current. Okay, you can determine the proper value of the Bn to produce the load current IL you want. No? So let's say I want a particular value of I of L. I can determine the proper value of Vn to produce this I of L, assuming that my BJT is in active mode. No? And actually, kanina pa natin ginagawa yun. Ano? So this is IB. So you have IB is Vn minus VBE over RB. Okay. And IL is just equal to beta times IB. No? So beta times Vn minus VBE over RB. So for the IL that we want, kung ano mang IL na gusto natin, we just have to adjust Vn. No? So you adjust Vn for the desired IL. You adjust Vn for the desired IL. Okay, ang problema, the problem with this particular circuit is that from transistor to transistor, your beta changes, even if it is the same part number. For example, a 2N2222 transistor, that's a very, very popular transistor. The beta is approximately equal to, I think, 200. But if you take a look at the data sheet, it can be anywhere from, let's say, 150 to 250. They will not guarantee it to be close to 200, even if that's the typical value. No? So this varies greatly from transistor to transistor, even if same part number. So see Dr. Sison, okay, explained that if you want a more stable current source, iba yung sinasuggest niyang circuit. No? Imbis na itong circuit na to, ang circuit na sinasuggest niya ganito. You have Vn then I have Re, and then this is my load. Then VCC. This is my I of L. Okay. Paano ito naging more stable? Paano ito naging more stable? No? Let's try to compute for I of E. Okay, I of E is V sub E over R sub E, no? Where this is the value of V sub E. V sub E is the value of your voltage at the emitter. Okay. But V sub E is V in minus VBE. So ito yung VBE. So the voltage here is the voltage here minus the voltage drop across my phase emitter diode. No? So VE is V in minus VBE. So this is V in, if this is silicon, 0.7 volts, no? For silicon. Okay. So this is now going to be V in minus 0.7 over R sub E. Okay. I load is just I sub C. Okay. But if you recall here, okay, if beta is very much greater than 1, I sub C is approximately equal to I sub E. No? No? But if beta is very much greater than 1, I sub C is approximately equal to I sub E. No? Therefore, my I load is just equal to V in minus 0.7 volts all over R sub E. If you take a look at this is not dependent on beta. My load current is not dependent on the beta of the transistor. Okay, it just depends on VBE and RE. And VBE is usually quite stable. Hindi kagaya ng beta, no? Beta can vary a lot. Yung VBE natin is quite stable. Tsaka hindi natin maiiwasan yung VBE, no? Because even in this case, meron pa rin tayong VBE rito. So our load will always be dependent on VBE. So this is a better current source. Okay. Did you understand the point I'm trying to make here, or the point that Dr. Season was trying to make? Okay. I don't know if this will interest you, no? But minsan nasira yung LED light, yung isang LED light ko rito sa bahay, no? I had an LED lamp, and it wasn't working anymore, so I decided to take it apart. And what I saw inside the LED lamp was something that was very similar to this, ano? So ang nakita ko, no, your 220 volts was rectified, no? That was your VCC. VCC is equal to 220 volts AC rectified, ano? So alam na nyo kung ano yung rectifier, ano? It converts AC to DC. And then here were all my LEDs. Dami, no? Many LEDs. And then all that was below was just a transistor with an RE and a fixed voltage. Here was a fixed voltage. The fixed voltage was, later on you're going to learn about reference voltages, but the fixed voltage was established using reference voltage. Now, why was the circuit like this? Because your LEDs like to be driven by a constant current. ang gusto ng LED, especially the LEDs for lighting, they like this current to be constant. Constant. So that constant current can be established by this. What is the current? What is this? What is this current? This current is just your voltage minus 0.7 divided by RE. So this RE actually establishes that current. It doesn't matter now how many LEDs I have here. In fact, it was the same circuit. I noticed it was the same circuit for a bulb with 20 LEDs and a bulb with 10 LEDs. It won't matter because regardless of the number of LEDs here, as long as your supply voltage is large enough, and this is very large, no? Itong supply voltage is very large kasi yung 220 volts rectify. Doesn't matter how many LEDs you have there, you just have the same current that will flow. So you will have the same brightness coming out, whether it's 20 LEDs or 1 LED. That's there. So anyway, that's just something on the side. So if having instead of having a base resistor, you have an emitter resistor that makes your current source more stable. Actually, it also makes your amplifier more stable. No? So an alternative amplifier circuit is something like this. You know? RE, RC, VO, VCC. Okay. And this is now my VIN. So my VIN now will be something like that, and my output will be something like this. And if you try to work out, if you work out delta V out over delta V in, okay, this is not dependent on beta if beta is very much greater than 1. And you can try working that out by yourself. Okay, I have in this particular slide deck some exercises for you to do. I don't want to go through them anymore. A lot of these are quite similar to the examples that I gave. So I just leave this for you to try on your own. And the answers are here. So for example, here, determine the required value of RB so that VO is 1/2 of VCC. No? BBE active 0.7, beta equal to 100. The answers are all here. No? So I have here 4 exercises. So I just leave you to try this out on your own. No? Are there any questions? Any questions? Okay. I hope you've been able to keep up. Mel, no? I hope medyo nakakahabol ka ng konti.
Yes, sir.
Okay. Sige, so I'll stick around just in case you might have questions. Otherwise, no, I'll stop the session already. Okay, thank you.
Thank you po.
You're welcome.